Okay, up till now, we have graphed our trig functions of sine and cosine, and you showed me in the previous work that you have done that you're able to handle the capability of graphing the sines and the cosines. What we have not graphed is we have not graphed the reciprocal functions and tangents and cotangents. And that's what we will work on today and continue on to next week. And how do we graph the ideas of a cosecant, of a secant, of a tangent, and a cotangent? Now, if you think back to what we just did with the graphs of sines and cosines, we will be utilizing the graphs of sines and cosines to be able to guide us through all of our graphs of secants, cosecants, tangents, and cotangents. So that knowledge of graphs of sines and cosines that you just dealt with, we'll be utilizing that knowledge again. If we take a look at, we want to graph the concept of y equals the cosecant of theta. We want to graph cosecant of theta here. So if we label our axes here for the cosecant of theta, how do we deal with the graph of the cosecant of theta? Well, how do we deal with the values of the cosecant of theta? Well, how do we find the values of the cosecant of theta? By definition, the cosecant of theta is equal to 1 over the sine of theta. The cosecant of theta is equal to 1 over the sine of theta. So to find the cosecant of theta, we had to just take 1 over the reciprocal, or we had to just reciprocate the sine of a value. So if we just take a look at a value here for 45 degrees. If we find the sine of 45 degrees, clickety-clack in our calculator, you get a value, a decimal equivalent of 0.707. Correct? And some change. To find the cosecant of that, we have to reciprocate this, which means 1 over 0.707, but your calculator is equipped with an x to the negative 1 power. If you just hit that button, what it will do is it'll write ANS and put to the negative 1 power. What that's going to do is it's going to reciprocate your answer that you just did. So if you hit the x to the negative 1 power and hit enter, you should get the value of 1.414. What I want you to do is I want you to go through, take the sine of this value, then reciprocate it. And if you get an error, which you'll get in the first one, you'll get an error. That's fine, just write an error here and put an empty set there. And we'll talk about it here in a minute. Okay, so go ahead and find these values here. Find the sine of 90, then reciprocate. The sine of 135, then reciprocate. Sine of 180, reciprocate, and so on down the line. And then I want you to graph theta y over here, just for the cosecant value, not the sine value, but the cosecant value. Go ahead and graph those points. So if we go down our values over here for the cosecant, we got air, we have 1.414, just keep going down the column.
I've got 1.41. Error, -1, error, 1, -1.
All right, so what I put up here is I put up our graph, because we're using the sine of theta. I put up here a graph of y equals sine of theta, where our amplitude is 1 period of 360, vertical horizontal phase shift is equal to the value 0. We just have a very general sine curve, y equals sine of theta here. Because it's y equals sine of theta, it guided us to finding our trig values for the cosecant of theta. It's also going to guide us to be able to get a graph of the cosecant of theta. So if we take a look at some values here, when we had the value of 0, we're in air. When we're at 45, we're at 1.414. Then at 90, we are at 0. Then at 135, we're at 1.414. Then we have an air. Then we're down here at -1. We have an air, we're back up here at 1. If I would take 30 degrees, and I would take the sine of 30 degrees, it would take the value of 30 and then take the sine of 30, and then reciprocate that, we should come down to a value of 2. Sine of 30 is equal to 1/2. We reciprocate it. The cosecant of 30 would equal a value 2. So at this value, we would come up to here, and we would start having some reciprocal ideas. The question is, graphically, what happens at these values here? Well, why we are getting an air is over here we take the value of the sine of 0, we get 0. And then we try to reciprocate this, we get 1 over 0. And what we've learned in our math career is, we can't have 0 on the bottom. 0 on the bottom of a fraction is a no, no, no. Okay, so we cannot have that. Well, graphically, what will happen, or what happens with a graph when we're undefined? What occurs here, and to be more specific, we get a vertical asymptote. Now, what an asymptote is in a graph is a line that is approached but never crossed. And typically they're lines. They're lines that are approached, which means when we're approaching it, we're getting closer and closer and closer to it. But we're never crossing it. Okay? We're going to get closer and closer to this, but never crossed. How we represent this on a graph is by a dashed line. So if we look at where we have our errors, we have an error at 0, so we're going to put a dashed line there. We have an error at 180, so we're going to put a dashed line there. At 360, we have a dashed line there. And if we look at our graphs of our guide function, our sine function, this occurs at these values here where we cross our neutral axis. Our neutral or our prime axis. Where we cross our neutral or our prime axis, we get these vertical asymptotes. Well, what's the rest of our graph look like then? Well, if we take a look at this section right here, I got a bunch of points here. These are lines I'm going to approach but never ever cross. So I'm never going to cross this line, I'm never going to cross this line, but my graph, I'm starting to become a little bit of a smiley face out there, which is sort of like a parabola. If you think back to the ideas of a parabola. We will approach this line over here, but we will never cross it. We will approach this line over here, but we will never cross it. What I will call these is I will call these asymptotic parabolas. And from this peak here, we have an asymptotic parabola going upwards. Well, when I switch to this section here, now I have this value right here. And if I would take the value of 225, a value of 315, what will happen is I will start to creep the other direction. So we will get our asymptotic parabolas going downwards. So we look at where we throw in our asymptotes. And where we throw these asymptotes, these will guide our functions now. What will guide our asymptotes is our reciprocal function. Wherever we cross here, we're going to get a vertical asymptote. We can draw in our sine or cosine curve. Where we cross here, we draw our vertical asymptotes, and then we have our asymptotic parabolas. So if we look at this cosecant, the cosine, we're going to look at the graph of the secant. Now we're not going to do all of our values here. We're just going to look at y equals cosine of theta. Our amplitude is 1, period of 360, vertical, horizontal, phase shift are both equal to 0. A very general equation here. And what we want to graph in here is we want to graph y equals cosine of theta. Okay? Which means we prime axis here, horizontal phase shift tells us our theta start value. We start at 0. Amplitude, since we're dealing with cosine, we start at our peaks and valleys. Okay, so all the cues that we utilized in regards to our cosine function, graphing the cosine function, we're still going to use them. Okay, theta start value, 0. Prime axis, 0. Cosine, peaks and valleys. So we're going to start at a peak at our amplitude of a value of 1. Okay, we deal with this first. We also have to deal with that. We have our trig function up here. Then we come here. Cosine at a period is 360. So if I'm at 0 and a positive 1, at 360 we'll be at a positive 1. And then we play our games of halves between 0 and 360. 180 we'll be at a valley at 180. At -1, and then we'll cross our prime axis, neutral axis at 90 and 270. So here would be our cosine curve. As we related everything, sine and cosine were together in regards to graphs. Secant, cosecant is going to be the same way. We're going to get our graph of our cosine function. Okay? Or the sine function. Next thing we're going to draw in, we're going to draw in now our vertical asymptotes. So wherever we cross our prime axis, our neutral axis, we'll draw in our vertical asymptotes. So our neutral axis is at 0, so at 90 and 270. At 90, 270, we draw in our vertical asymptotes. From any peaks, we're going to get asymptotic parabolas going upwards, and any valleys, asymptotic parabolas going downwards. Well, we're just going to look between 90 and 270 right now. Between 90 and 270, we got two asymptotes here. I have a valley, so I'm going to go downwards, and we're going to go downwards. That gives us half of the graph. The question is, how do we get the other half here, the ones going upwards? Well, you have two options. The first option is do two half parabolas. So I could go one half over here, the other half over here. So we have two halves. Or if we wanted to, we could draw in another asymptote. I got an asymptote at 90 and 270. Going this way or going that way, where else would be another asymptote? If I went this way, where would be another asymptote? -90. So at -90, I would have another asymptote here, and then I could finish my parabola. And out here at 450, this would come back down around, and I could draw in one out of here if I wanted to, and finish my asymptotic parabolas. Either way is correct. You can do two half ones, or you can find another asymptote. Doesn't matter. But the key is the guide for the secant. The guide for the secant is our cosine. The guide for our secant is our cosine. The guide for our cosecant is our sine, the reciprocal functions. Okay, it gives us two of the reciprocal functions. Let's take a look at tangent and cotangent. By definition, tangent can also be defined to us, and we'll eventually get to this a little bit more, as the sine of theta over the cosine of theta. If we would take the sine of 30 and divide it by the cosine of 30 and hit enter, and then take the tangent of 30 and hit enter, you're going to get the exact same value. Try it. Take the sine of 30 divided by the cosine of 30 and hit enter. Okay? Then the next line, take the tangent of 30 and hit enter. You get the same value. And the reason why, we have opposite over hypotenuse divided by adjacent over hypotenuse. Opposite over hypotenuse divided by adjacent over hypotenuse. If I flip and multiply, we have times hypotenuse over adjacent. The hypotenuse, they cancel out, leaving us with opposite over adjacent. So it just comes back to it. So what guides our secant and cosecant functions in the graphs of the cosecant secants were where I drew my asymptotes in. Well, where you draw your asymptotes is what makes the bottom equal to 0. What makes the bottom equal to 0 gives us our asymptotes. So if I'm looking at graphing this tangent, we need to use the cosine as the guide. So if we look at the graph, 90, 180, 270, 360, we have our theta and we have our y, and we're graphing in the cosine. It's the same graph we just did. We still get our same graph. Okay, amplitude of 1, period of 360, vertical horizontal phase shifts both of 0. We're still going to draw in our asymptotes. Wherever we hit the prime axis, neutral axis, we're still going to draw these in. So we still have asymptotes of 90 and 270. It has not changed yet. What changes with tangent and cotangent? When dealing with the secant and cosecant, we have the asymptotic parabolas, which are here. You have your asymptotic parabolas. You have a U shape in your graph. Okay, that is square functions, quadratic functions. When we look at tangent and cotangent, it turns into cube functions. Well, when I turn into cube functions, what happens with the parabola when I turn it into a cube function and talk about x cubed rather than x squared? This gives us y equals x squared. We just scored a touchdown. Okay? When I go into a cube function, we drop one arm down to here. This is your cube function. This is your square function. Cube, square, cube, square. All right? So we have a cube function. Rather than turning and going upwards up here, we just turn it and go the other direction. That's your idea of a cube function. Parabola, we just keep going with this U. We take this arm and we turn it the other way. Well, when we're talking about tangent, we go from upper right to lower left. Upper right to lower left with the tangent. Halfway point. We cross the prime axis. My halfway point between 0 or 90 and 270, here's our halfway point right here. And we go from upper right to lower left. Once again, rather than do it with a parabola that would turn and go back upwards, we just turn it and go the other way to make it a cube function, an asymptotic cube function. Now, if we wanted to, we could draw another asymptote, but we don't really have to, because we would have an asymptote here, and we would have the exact same graph over again. So we don't really need to do a second one there. The reciprocal to tangent is cotangent. So this is cosine theta over sine theta, the reciprocal. So what we're going to use as a guide function is now the sine. So we want to graph y equals sine of theta. Vertical horizontal phase shift both equal to 0. Amplitude 1, period of 360, everything's the same. Sine curve, we start on the prime axis. So we have our sine curve in there. Wherever you cross the prime axis, draw your vertical asymptotes. And this would go from upper left to lower right, just flips it over. We still hit the halfway point, hit the halfway point. And once again, we don't need to draw both of these in, but we can. If I have asymptotes there, I usually do. Okay, lastly, let's go to what happens when we change out of theta into x. Now we're dealing with things in radian ideas. And believe it or not, it looks a little confusing here to begin with, but it is a little bit easier because our numbers get smaller. Cosecant function, what will we use as a guide? Reciprocal to cosecant is sine. What's our amplitude? Well, look at our coefficient here. We're going to use sine as our guide. Amplitude is a value 3. Vertical phase shift, we have a value of 2. Horizontal phase shift, we have a value of 1. Now the problem we run into is our B value is pi over 3. Period was calculated by 360 divided by our B value. Since we are dealing with radians, period is now 2 pi divided by this B value. So we have 2 pi divided by pi over 3. Dividing a fraction, we flip and multiply. 2 pi times 3 over pi. And what happens nicely is the pi's go bye, bye, bye. So we have a value of 6. 2 times 3 is 6. Numbers get really small, which is nice. Yeah.
Could you do, so you know how you said that you could do like 180 divided by 3? Or like you just said,
360 divided by B?
or no, wait. Because I did it in my calculator.
What'd you get?
I got 62. When I did 180 divided by 3, I got 60, and then I just did 360 divided by
You can do that.
60. Okay.
Don't let the buddy above your head watch you because he may call the popo.
Okay.
And but
I'm sorry.
they don't like when you divide degrees by degrees, but it does work. What she says, pi over 3 is 180 divided by 3, which is 60. If you take 360 divided by 60, you still get the value of 6. It works. But like I said, good old buddy Pythagoras could have a conniption on that. Let's see, getting our graph down. But it does work. We have an amplitude of 3, vertical phase shift of 2. We have a period of 6, which means this makes numbers a little bit easier. 1, 2, 3, 4, 5, 6. Once again, the nice thing about dealing with things in radians, numbers get really small. It's a little bit easier, something a little bit more comfortable for us. Drawing your prime axis. Our Q's are not going to change. Drawing our prime axis. Where do we start? Horizontal phase shift, trig function. I'm going to have to probably go up to 7 here. Start at a value of 1 on the prime axis because it's a sine curve. Period now is a value of 6. So every 6 spaces, I'm going to be at the exact same spot. So at 7, I'll be there. Games of halves, halfway between 1 and 7. 4. Halfway between 4 and 1. 2.5 will be at a peak, which is up at 5. And between 4 and 7 is 11. 5.5 will be at a valley at -1. Wherever I cross the prime axis, vertical asymptotes. And then from any peak, asymptotic parabola up, valley, asymptotic parabola down. It's because we're talking about cosecant. We will have more practice with this on Monday and also Tuesday. Okay. The cues that we have with our strict functions, you'll see over and over and over again. All right, our homework, our notes on Monday will be working notes from our homework for today. So if you can get some of them done, try to get some of them done. We'll utilize them as examples in our notes as we lead into worksheets next week. Okay, nothing new. Everything we've done now will be on our next quiz. We won't do anything new on our next quiz. All right, questions? All right, I am done.